All right, hi. This is my 75-minute, hopefully, presentation on the dial-a-ride kinds of problems that arise in scheduling for my comprehensive exam. So what is a dial-a-ride problem? Well, in a dial-a-ride problem, what's typically happening is we have some sort of city where we have customers who need to get from their starting location to their ending locations by a fleet of vehicles. So for example, maybe we have some sort of depot, and then let's say we have maybe 4 customers. We have a customer 1 who wants to start at a location, and then maybe get to a different part of the city. And so we'll label plus as the starting point of the customer, and minus as the ending point of the customer. Maybe we have another customer who's going to get picked up here, wants to get dropped off here. A third customer wants to get picked up here, dropped off here. And a 4th customer who wants to get picked up here and dropped off here. So a classic example of this would be elderly people in cities. Like even Tempe has this sort of program where if you're an elderly person and you need to get around, the government will actually have a fleet of vehicles that'll transport you when you call them up and request a ride. So there are a couple different ways you can sort of model it, depending on what constraints the customers have. For instance, the customers, maybe they called in all at the same time, and then they all called in, and then you have a vehicle who's ready, and the vehicle is going to leave and serve all the customers. So that's sort of like a static problem where all the customers are set in advance, and then the vehicle is going to come pick them up. Similarly, you can have a dynamic case where the customers call in as the vehicle is moving, so the problem has to update itself as vehicles progress. You could have one vehicle leaving from the depot, just a single van, which I'm going to draw right here. Or you could have a fleet of vans that are all going to serve these same customers. And then you have to sort of balance the fact that vehicles are going to be in certain locations, so you want to kind of group customers by proximity, but at the same time you also have time constraints. Speaking of which, these customers, they could also call in and say, hey, I have a dentist appointment at 10:30 I need to get to, so it doesn't make sense, or I need to be there by a certain time. Or similarly, I don't want to leave until at least this time, so I'm going to make it a reservation in advance. So there's time constraints. There's also ordering constraints. You could have it that customers call in, the numbering of the customers may be the order they called in. And a customer may not want to be, if the earlier customer shouldn't be should be handled before a certain number of later customers. So the first customer can't be dropped off after the 4th customer is picked up. So you can have these sort of ordering effects as well. So there's a lot of constraints, and the question is, what are you trying to optimize? Well, again, it depends on your situation, but the simplest thing to think about is you kind of want a linear combination of 3 things. 1, the total distance the vehicle is going to travel, or fleet of vehicles, depending on how many vehicles you have. You may have these vehicles, the drivers may have salary, there may be fuel costs, so you want to minimize how far they're traveling. Similarly, you want to minimize how long each of the customers is waiting, because the longer the customers wait, the more upset they are. And of course, you also want to minimize how long the customer is in a vehicle, because maybe I'll pick up a customer real quick, but then the customer has to sit in the vehicle as the vehicle goes and picks up other customers. So you have to balance the waiting time of the customer with the travel time of the customer. And of course, these vehicles aren't infinitely large, so you have to, an additional constraint is the fact that each vehicle is going to have a certain capacity. And so all these different problems are all fall into the field of dial-a-ride problems. So today I figured, first thing, we'll walk through the case, what's the most simple case. So the simplest case is you have one vehicle, one depot that the vehicle is leaving from. You have a set of customers, those customers are determined before the vehicle leaves, and the vehicle is going to go and try to serve all the customers. Let's say that the vehicle has some fixed capacity. So for this kind of a problem, a solution example would be, let's say my vehicle starts at the depot. The vehicle is going to travel to the first customer, pick them up. The vehicle is going to travel and pick up the second customer, drop off the first customer, pick up the third customer, drop off the second customer, drop off the third customer, pick up and drop off the 4th customer. Now when I was drawing these lines, I didn't actually have the car go back to the depot. So the formulation I'll be dealing with today, we'll just assume that once the vehicle drops off the last person, we're done carrying. You could just as easily add the fact that part of the cost is also the car returning back. It's just 6 of one, half a dozen of the other. And notice that the vehicle never had more than 2 customers in it. Also, worth noting, this is just something I drew. I don't know if that's actually the optimal solution. It depends on how long each of these legs are. And again, maybe if we assume that the distance length of the leg is the length of the line on the board, probably the best solution. I don't really know, I didn't actually solve it. Just kind of hand-waved. Okay, so this formulation, this one car picking up all the customers at the same time formulation, it was dealt with in a paper by, I'm going to try and pronounce this guy's name right, Svartis, from MIT back in 1980. So this is kind of old hat, but this is still a problem that's being worked on today. This is just the most simple implementation. We're going to try and solve this, or we are indeed going to solve this to get an exact solution. However, today most of these problems are being done with heuristics just because real-world problems can't be solved exactly. And why can't they be solved exactly? Well, it turns out this problem's NP hard, even in the case with just one vehicle and a set of customers. And so why is the problem NP hard? Well, it can actually be, you can have a traveling salesman problem can be reduced to the dial-a-ride problem. So the dial-a-ride problem is at least as difficult as the traveling salesman problem. And how do you do it? Well, let's say you have a traveling salesman problem where I have 5 points in the traveling salesman problem. 1, 2, 3, 4, 5. The way I can turn a standard traveling salesman problem into a dial-a-ride problem is I make one of the points the depot, I make the rest of the points customer pickup spots, and then I have the drop-off spots for all the customers be in the depot. So all these customers are going to be picked up and dropped off where the vehicle needs to return to. And so now any solution to this dial-a-ride problem is also a solution to the traveling salesman problem. So provided the objective you're trying to minimize is the total travel time of the vehicle, in that case it's the exact same as a traveling salesman problem. So if I could solve the dial-a-ride problem in polynomial time, I'd also be able to solve the traveling salesman problem in polynomial time. So that just goes to show that this is not going to be something, if we have hundreds of customers throughout the day with lots of constraints, it's not going to be something that can really be done explicitly, or exactly. And in fact, so far as I know, as of 2005, I think, the exact solution for the dial-a-ride problem had only been solved up to 9 customers. So this isn't really something that's been too well established. Okay, so the way we're going to try and solve this problem is we're going to be using dynamic programming, a dynamic programming solution. And before we do that, let's just talk about exactly what are our constraints. So first off, let's talk about before we go to our constraints, I'm getting ahead of myself, let's talk about the objective function. So as I said, it's going to be a linear combination of the travel times, the riding times of the customers, and the waiting times of customers. Specifically, we're going to write it as this. Where n is the number of customers to be served. So here's our objective function. We're trying to minimize this. Where, okay, so W1 and W2 are just weights. And they're weights that we use to determine the how much we care about the T of J, which is the travel time of the jth link in the route. So link, i.e. edge. So this would be the first link, second link, third link, fourth link. And if you figure there are n customers, let me put that up here, n customers then there are going to be 2 end links because we don't have to go back home. So there's 1 link for to pick up every customer plus 1 link to go and drop off every customer. So TJ is the travel time. WTI is the waiting time of the ith customer. And RTI is the waiting time, is the travel time of ith customer. And alpha is going to be the customer's time preference. So 0 is less than or equal to alpha, less than or equal to 2. So if you look at, so let's just go back to the top here. So I'm trying to weight between the amount of traveling that the vehicle has to do, T of J, so traveling for each one of the links. And I also have to take a penalty for all the time that the customers take. So how long the customer has to wait around and how long the customer has to ride. This alpha business, which looks kind of weird, the whole point of it is that the customers are going to have a preference between how long they're going to want to wait and how long they're going to want to ride. I personally would rather be waiting for the vehicle to pick me up than I would be inside the vehicle, because at least I can watch TV or something. So if that's the case, then I would have a low alpha because I'd want a lot of weight on the riding time. The reason why we do this business with the 2 is because we want anyway, so we have a couple constraints. So first off, here's the big one. A customer needs to be picked up before being dropped off. So my solution is going to be a set of links that the vehicle is going to take, but it doesn't make sense for me to go to the drop-off point of one before I pick up one. So any one of my solutions, for it to be valid, it has to be a sequence where the plus version of a node falls before the minus version. 2, no more than C customers can be in the vehicle. Right, so the vehicle has some size, you can't have more customers in it than however big it is. And 3, this is, I kind of alluded to earlier, there's going to be some maximum position shift. Some maximum constraints. So here in this problem, as I said before, the numbers of the customers are the order they've got dialed in. So any one particular customer is not going to want to be served either long before, it can't be picked up too far before it's ordering. So like customer 4 can't be picked up too many steps before customer 1, and they can't be delivered too much later. Or a customer can't be delivered too much later than their number in the ordering. So specifically write that as I minus PI is less than whatever my MPS constraint is. And similarly, the I minus DI, the absolute value of that has to be less than whatever my maximum position shift constraint is. And so what this is saying is I is the number of the customer, and PI is the position of pickup in the order of delivery. So, for example, here the pickup for 1 is 1. The pickup for 2 is 2, 3, and 4. So it's in order. The drop-off actually happens to all work out in this problem too. But if I say dropped off customer 2, if I dropped off customer 2 before I dropped off customer 1, so if I had a slightly uglier route, now here the position of 2 in the drop-off ordering is 1. So here PI is the pickup order, or the position, pickup position of customer I, and DI is the drop-off position. So we have our constraints, we have our objective function. Now we can go ahead and talk about how we're going to do the dynamic programming. So for dynamic programming, what we need is we're going to try and build our solution up based on smaller solutions. So we need some sort of way of describing what the environment is. And so here, what our state is going to be of the form L and then K1 through Kn. So again, n is the number of customers, so I have some particular number plus a bunch of other numbers. But what do they mean? So L is going to be the location of the truck, or van, at a particular point in time. So these states are going to sort of, our solution is going to be a sequence of these states. So this is going to be the location of van at this particular state. And then Ki, for each one of these customers, so for customer I, is going to, so Ki is going to equal 1 when the customer is dropped off, or customer has been dropped off. Ki is going to equal 2 when the customer is in the car, or in the van. And then Ki is equal to 3 when customer still needs to be picked up. So with these n+1 numbers, we actually have a full description of the solution as it unfolds. So for example, this vehicle is going to start. Oh, sorry, I forgot one important point. The location of the van. How are we going to enumerate that? Well, L is going to be equal to 0 when we're at the depot. One is going to be less than or equal to L is going to be less than or equal to N when picking up customer L. And n+1 is going to be less than or equal to L, which is less than or equal to 2n when dropping off customer L minus n. So for instance, when L is equal to 0, we're at the depot. When L is equal to 3, we're picking up customer 3. And if, let's say, we had 4 customers, when L is equal to 5, that means we would be dropping off 5 minus 4, so we'd be dropping off the first customer. So here, like a start state, for instance, would be 0, 3, 3, 3, 3. Again, this is a situation where I have 4 customers. Because the vehicle is at our starting location, and all these customers need to be dropped off. Another state we could do is we could have, let's say, 2, then 1, 2, 2, 3. This state would say the vehicle is picking up customer 2. Customer 1 has been dropped off, customer 1 is all set. Customer 2 is in the car, which makes sense because the vehicle just picked up customer 2. Customer 3 is also in the car, and customer 4 hasn't even been dealt with yet. But as you can see, not all states are actually valid. For instance, if I did the state 2, 1, 1, 2, 3, so the same state as before if I just switch this. This say the vehicle is at location, pickup location of customer 2. But customer 2 has already been dropped off. So this would be an invalid state because I can't visit a state that I've already been to pick up a person. There's no reason to do it. So this one's invalid. And I talked about the start state. What's the end state? Well, the end state is going to be something, it's going to be some L, and then our goal is going to have all ones. And I guess specifically, this L has to be greater than or equal to n+1. So I have to have just dropped off a customer, and then have all of my customers be set. So now these are the states, and what we're going to do in dynamic programming is we're going to set a value for each one of these states, and then we're going to sort of build our way up until we find the optimal value for the starting state. And that'll be our our solution to the objective function. And let's think about this for a second. How many states are there? Well, there are n of these indices, and each of these indices take 3 values, and this one can take 2n values, 2n plus 1 values. So the number of states is 2n plus 1 to the 3n. And so, as you can see, there's an exponential number of states, and indeed the runtime of this algorithm is going to be, n to 3n. So it's an exponential algorithm, which makes sense because it's a NP-hard problem. And indeed, the runtime can't really be smaller than the number of states in this algorithm, because I'm actually going to have to go through and consider each of these possible states. So, as I said, some of these states are valid, like 0, 3, 3, 3 is valid, and 2, 1, 1, 2, 3 is invalid, I said just by looking at it. But we should more formalize what it means to be an invalid state. Once we do that, then we can sort of build our solution up by taking all the valid states and sort of working our way to find the value of the very first state. So for a state to be valid, it has to satisfy a couple of things. So for a state to be valid, first off, the state should be consistent. And by consistent, I mean it shouldn't contradict itself. So first off, if L is equal to 0, then that implies that Ki has to be equal to 3 for all I. Right? So the only time we're at the depot is before anyone's picked up. I can't pick up some people, do some stuff, then go back to the depot. If 1 is less than or equal to L, which is less than or equal to less than or equal to n, that implies that KL has to equal 2. So anytime I'm picking up a customer, I have to actually put them in the car. I can't go to a pickup location and have the customer already delivered or not yet be delivered. Getting to the place to pick them up means picking them up. And 3, if n plus 1 is less than or equal to L is less than or equal to 2n, that implies KL minus n has to be equal to 1. So, if I've dropped off a customer, that means they actually have to be dropped off. When I get to a dropping off point, the state of that customer whose dropping off point it is has to be dropped off. Okay, so that's the state has to be consistent, but we have more constraints than that. So we also have to have the vehicle should be within capacity. Not exceed capacity. So for this constraint, all I have to do is say that x2 has to be less than or equal to c. And you could do clever tricks where you only have to consider the capacity of the car when I'm dropping off customers, but don't worry about it. Just at all states, I can't possibly have a state where I have more people in the car or in the van than I have space for them. Next, I need to satisfy my maximum position shift constraints. And again, recall these are constraints on how far in the ordering of my customers will have to shift around. So the way you do this is when I pick up a customer, so if 1 is less than or equal to L is less than or equal to n, then L minus x1 plus x2 has to be less than or equal to MPS. So x1 is the same thing, but that's the number of KIs equal to 1. And I'll write that down just so you have it. And this is going to ensure that whenever I pick up a customer, I can't have already considered more customers than the allowable shift. So if I'm about to pick up customer 3, then I can't have already dropped off and have people in the car more than, the difference of that has to be less than my position shift. So if I'm picking up customer 3 and I've already dropped off one customer and one's already in the car, that would mean I've dealt with 2 customers before customer 3. So that's a shift of 1. So that's, that should presumably be fine, depending on what my NPS number is. Also, the vehicle routes have to be legitimate. Sorry, get my pages confused. And then similarly, I also have to consider the fact that n plus 1 has to be less than or equal to L. Or in the case when I'm dropping off a customer, I also have to consider my NPS constraint. So then it's L minus n minus x1 has to be less than or equal to NPS. So I can't, if I'm dropping off the 5th customer, I can't have already dropped, and I've already only dropped off 1 customer, that would be a high shift, because I'm dealing with a high number in the ordering by picking up the 5th customer, but I've only dropped off 1 customer before it, so that's a position shift of 4. So if my maximum position shift number is like 3, that would be a problem. So these are all necessary, but they're not necessarily sufficient. And the reason why is any one of these states, a state may satisfy all these rules, but it may so happen that if I'm in a state that satisfies all these rules, then the following states, the future states after that one, none of them may follow the rules. So if I'm in a feasible state, but I can't do anything beyond that's feasible, that would be a problem. So let's say we have a state so let's say we have a state L, K1, Kn, and I'm considering my next state. L prime, K1 prime through Kn prime. And just for an example of this, let's say we're back in our 4 customer world. So if the first thing I did was start at the depot, a valid next state would be to go 1, 2, 3, 3, 3. And this transition would represent going from the depot to the starting location, the pickup location of customer 1. So customer 1 is then in the car and everyone else is still waiting to be picked up. So if I'm in this state, my next state, it can follow, it has to fall into, the L prime has to fall into 2 sets. Fall into one of 2 sets. Either the set S3, which is the set of next pickup stops. So here, it's I such that 1 is less than or equal to I is less than or equal to n, and ki is equal to 3. So that's what I did over here. I went to one of the future pickup stops because here I was going to be equal to 1 because it falls in that range, and at that point K1 was equal to 3. So I can, wherever I am, I can go to a future spot, or a customer that, I can go to any customer that needs to still be picked up. I could also go to any next delivery stop. So union S2, or so I guess, yeah. So or L prime can fall into S2, which is going to be I, and so the set of customers, all of the drop-off positions of the future customers, and I can only go to a drop-off position of these customers if I currently have that customer in the car. So, for example, if I want to drop off customer 5, in my 4 customer world, or sorry, if I want to drop off customer 3 in my 4 customer world, then I would take an I value of 3 plus 4, which is 7. So I'd set L equal to 7, and that would be valid only if the 3rd customer is currently at 2. As in, the 3rd customer is currently inside the car. So that's how we find our new L prime value. And our new K prime is given by, so for each J value of this K prime, I'm going to have it, I'm going to subtract 1 from it if J is equal to L or J is equal to L minus N. And Kj otherwise. I'm sorry, this should be L prime. So the point is, if I go to pick up a new customer, then wherever that state I go to, I have to decrease that customer by 1. So if I go to pick up a customer, then that customer's state goes from state 3 to state 2. And if I go to drop off a customer, that customer is currently in state 2, so then it has to subtract 1 to go to state 1. And all the other customers stay the exact same. So for example, here, when I went to pick up customer 1, I decreased that value by, the value of customer 1 by 1, and all these stayed the same. So this would be a valid state to transition to. An invalid state would be something like this. So this is a bad transition, because here I went to pick up customer 1, but this index changed. So I can only change one of these customer indices at a time. It doesn't make sense. I can't go to the starting location of 1 and change the status of customer 1 and customer 2. So I can only change one of these things at a time. So at all times, the only time where I can't do at least one of these things, so if S3 is empty, that means that no more customers need to be picked up. And if S2 is empty, that means no more customers need to be dropped off. So if both these sets are empty, that means I'm done. I've successfully delivered all the customers. And in that case, that would be considered a valid terminal state. And in fact, the valid terminal states, as I think I said earlier, are states where all the indices of the customers are equal to 1, which makes sense because that would mean the set of customers that have 2s or 3s is not empty, or is indeed empty. So when we have a particular state, if I give you, like let's say before, if I just give you the state 1, 2, 2, 3, 3, the way to check if that state is valid is 1, I can check each one of these 3 rules. And then 2, I can check if all of the states that that it can lead to, all the next possible states are valid. If there's at least one valid state for this state to go to, then this state is fine. But if this state satisfies all these rules but can't go anywhere, that would be an invalid state. And so the solution here to try and figure out all the feasible states is you start with the set of all terminal states. So you start with the states in our 4 worlds. So you start with 5, 1, 1, 1, 1, 6, 1, 1, 1, 1, 7, 1, 1, 1, 1, 8, 1, 1, 1. These would be our terminal states. And these represent the order, which customer was the last customer I dropped off. Here this would be the dropping off customer 1 last, customer 2, customer 3, customer 4. I find that those are feasible, and then I work my way backwards and I determine which of the states before those states are feasible. And I work my way back from those and I build my way up to determining whether which of all these states are feasible. So once I have all these feasible states, how do I'll have a subset of these 2n plus 1 to 3n states. A subset of these are going to be feasible and satisfy all the constraints. So how do I determine what sequence is the best? So if I have a sequence of states, I start at state 0 through 3, I go to state 1, 2, 3, 3, and I go to a different state, and eventually I get down to here. One of these sequences is going to have minimum cost. How do I determine which sequence is the best sequence, and what is the cost of that sequence? Well, it's actually fairly straightforward once I have all the states. Because let's say I have a state, I'm in a state S, and my state S can lead to S1, S2, S3, or S4. Well, I can determine the value of each of these states, and the value for, the value for the initial states are 0. Or sorry, the value for the final states are 0. And then the value for any of the other states is just dependent on the travel time between my current state. I set these minimum, these values equal to 0 for this one, values equal to 0 for this one, values equal to 0 for this one, values equal to 0 for this one. So then now let's say I'm considering the state, let's say I'm considering the state, let's say 2, 1, 2, 1, 1. So this is a state where all the customers have been dropped off except for customer 2 who's currently in the car. Well, the distance, this state can only lead to dropping off customer 2, which would be this state. And the distance between the pickup point 2 and the drop-off point of 2 is something I know. That's something I can look at my input data and determine what those distances are. So the value of this is going to be whatever the distance is between point 2 and point 6, plus the value of this one, which is 0. Since there's no other points that I could possibly go to from here, that's fine. If there's a possible set of all different points I could go to, I just take the minimum of all those. And so that's the value for this one, and I build up my way, starting from the ending nodes, I kind of build my way backwards until I get the value of my starting node. And that's the value, that's the minimum value solution. And the actual solution sequence is whatever path from the whatever end state you chose all the way to here is optimal, or is chosen to get that minimal value. So that's how you do the one vehicle static problem where all the customers are known in advance. There's actually a nice trick to get the dynamic case where customers can be added to the problem where customers can be added to the problem in a dynamic way. And how do you do that? Well, let me draw my diagram from before. So I have a depot at the pickup location of 1, pickup location of 2, the drop-off location of 1, the drop-off location of 2. So it's maybe slightly different. The pickup location of 3, pickup location of 4, the drop-off location of 3, and the drop-off location of 4. So let's say this is my problem. And so let's say, so this is slightly different before. Let's say here, I've determined this solution. And again, now let's say I'm considering the case where these vehicles may get new customers during their route. So someone may call up and say, hey, pick me up 2. Well, let's say that happens with I picked up customer 1, I picked up customer 2, and then right when I'm here, I get a telephone call that says, hey, here's customer 5, deal with customer 5 as well. Customer 5 is going to be picked up here and dropped off here. Well, what I can do is I can say, okay, now this is a new problem, where my new problem is, I'm going to say, this is my depot. I'm going to say my starting state is now I'm at the depot, and 2 is already in the car. Or 2 and 1 are already in the car. And I say, forget this part of the problem. The van starts with 2, here's my van. Customer 2 and customer 1 are already in the van. And now erase my old path, and now solve this problem. So that solution I had before using dynamic programming with all the different states, I can use that exact same process again. The only difference is I'm going to have a different starting state, and now instead of my starting state being 0, 3, 3, 3, 3, 3, because this is a 5-person case, my starting state is going to be 0, 2, 2, 3, 3, 3. So that's my new starting state, because I already have customers in the car. So the same techniques in the static case can be used in the dynamic case. And that's sort of a simple case of the dial-a-ride problem, perhaps the simplest with the minimum number of constraints. For the more complicated problems, like say each customer has a time at which they can't be picked up before a certain time, because let's say they put a reservation in for like an afternoon doctor's appointment. You can add those sorts of constraints to these exact problems, and you can even add different multi-vehicle problems. You can modify those as you want. The issue is that the more you modify it, the more and more complicated your solution techniques are, and it very quickly becomes the case that your exact solution isn't really feasible to solve in real time. Especially if you have something like this, where your customer base will be changing dynamically. So you're going to need to generate solutions real fast as more customers come in. Or worse, if some of the customers you were planning to pick up suddenly called and canceled. So the papers that are being dealt with today more have to do with how do you heuristically solve these sorts of problems. And so one last thing I'll talk about is sort of the simplest heuristics, especially for the multi-vehicle case. So these heuristics started being worked on in the 80s. They're still being improved upon today, but the simplest rules work something like this. And this is for the multi-vehicle case. Because that's typically, if you think about a city that's dealing with lots of customers, the multi-vehicle case is going to be the one that's much more realistic. So the multi-vehicle heuristics basically work something like this. So you have n vehicles. So you consider each customer in some sort of sequence. Maybe they're starting the sequence they called in, maybe they reverse the sequence called in, it doesn't matter. For each customer, check to see, so for each customer I, let's say, each customer I, check to see if vehicle J can service it. So if I have 10 vehicles and I have customer number 5, I'm going to try assigning customer 5 to each vehicle and see how much that costs. So once you've done that, or I guess for each customer I, see if the vehicle can serve it, each vehicle can serve it, see how much it costs, and then assign the customer to the cheapest vehicle. And then repeat. So if I have 10 vehicles, I'll say customer 1, I'll assign you to vehicle, or let's say I have 100 customers, 10 vehicles. Customer 1, I'll assign to the first vehicle. Customer 2, I'll check. Can I assign it to the first vehicle and still serve customer 1 who's already been assigned there? If yes, consider it. If no, just assign it to a new bus, or a new van. Repeat this again, repeat this again. Let's say I'm at customer 50. Can customer 50 be assigned to vehicle 1? Well, bus 1 or van 1's already dealing with customers 1, 7, 13, and 42. So given those sets of customers, it's not even feasible to get this customer served by that bus as well, or van as well, given the particular time constraints. So you just iterate through, check if the vehicle can service it, assign the customer, repeat, until all customers have been serviced. Now, this is not particularly clever. There's not some big trick here. It's just sort of build your way up. And the issue with this approach is, depending on how your customers are ordered, you may end up with a much less efficient solution than the truly optimal one. But the good news is this is extremely fast. You just consider each customer once, so it's linear in the number of customers. A lot of more modern day improvements have to do with sort of clustering the customers and say, well, these customers are all sort of close to each other, so they should be serviced by the same vehicle. These customers are close, but then you have this issue where these customers are close in proximity to each other, but they're not close in time. So you have to sort of balance out the fact that customers may be close, but they're starting this because of when they put the reservation in the system. It's not going to actually produce a solution that has that bus being used efficiently because it'll be idling a lot, etc. So that's sort of where the state of the art is going today, and even more modern techniques, like genetic algorithms, meta-heuristics are being used on the dial-a-ride problem as well. But beyond the sort of simplest cases, it doesn't really work that you can solve it exactly. So that's sort of my overview on the dial-a-ride problems. I guess if this were a lecture I was teaching, I would be asking the students now if they had any questions, otherwise thanking them for their time. So thank you.